Today, we're very happy to have Amichai Lampert from New Michigan to speak to us about polynomial bands for Birch theorem on forms. Yes, please.
Thank you. Thank you for the invitation to speak. It's a pleasure to be here.
No.
Sorry?
Terrible color.
Okay. Just for the title. Not even for the title. Okay. Polynomial bounds for Birch's theorem. Before I get into which theorem of Birch's I'm talking about, I'll just start with a very old question. So given some three rational numbers, not all zero, sorry, all of them non-zero, does this equation have a solution over Q? And I mean a non-zero solution, right? This is a homogeneous equation. And so, of course, there's various examples you can have. So Pythagorean triplets have infinitely many solutions. There's some examples where you don't have solutions. For a reason of a local obstruction, or maybe another kind of local obstruction. There's also examples where you don't have solutions for more interesting reasons. Right? So here's a famous example of Selmer. Where there's no local reason for this equation not to have rational solutions, but there is a global obstruction. Okay, this is just sort of for flavor. Of course, a very famous result in higher degree is Balding's theorem, which says that if the degree is greater than 3, then maybe you have rational points, but at most finite. All right, so there's all sorts of different behavior that we can have in this case. On the other hand, the setting that I'm going to be talking about today is when the number of variables is substantially bigger. So here's a typical example. There's a theorem of Baker from '89, which says that the equation A1 x1 cubed up to A7 x7 cubed equals 0. This one always has a solution over Q. And this getting this number down to 7, this 7 is tight, so in 6 variables you might not have a solution. I mean, I'm citing the results from '89, but this is sort of the culmination of there. Okay, so this is sort of typical of the situation I'm going to talk about today, is that when you have sufficiently many variables, then you always have rational points. And the proof of this result is uses the Hardy-Littlewood circle method. So this uses analysis, harmonic analysis. Okay. So here is a more so this is in degree 3. Here's a more general result of Peck from 49. And maybe the attribution should be earlier, but this is the earliest attribution I found. So Peck shows that if D is odd, and n is sufficiently large, depending on the degree, then a diagonal form of degree D, the D, always has a Q solution. Okay, and I'm going to stop writing solution over Q soon and just write solution. This is again using the Hardy-Littlewood circle method. So you get this result for diagonal forms. But a few years later, Birch took this much further. So now I'm going to give sort of the general setup for today. So our general setting is E is some odd degree, and F1 up to FR are homogeneous polynomials of degree D.
They're all of the same degree.
They're all of the same degree. That's not going to be important. They can have different degrees in the results they state. Although maybe, yeah. But for now, I'm just going to take them the same degree. Birch proved in 1957 that in this situation, so long as the number of variables is greater than some threshold, depending on our two parameters, then the system of equations Fi equals 0 has the solution of Birch.
Get infinitely many.
Well, you can sort of deduce that if you increase them, say, increase it to twice this number, you'll have infinite, or yeah.
You did,
Yeah.
linear spaces of solutions.
Well, yeah, I mean, yeah, you're asking about projectively infinitely many, I presume. Yeah. But yeah, you can. Yeah. Oh, actually, a nice argument I learned recently from David Kashdan, very simple argument. If you have a result like this, then if you increase your dimension by say 1, then every subspace of this dimension is going to have a rational solution. And so you get that the dimension of the solution set is at least 1. But yeah, I'm not sure that argument appeared at the time implicitly or explicitly anyway.
You actually found linear spaces of solutions, so that automatically gives.
Yeah, right, yeah. Oh, yeah, I see what you're saying. So
It's hard to imagine him using. Well, because he might be pushing it, and projecting.
It's got linear spaces of solutions, or you've got any dimension. So it's automatically.
okay, so Birch's theorem uses an elegant diagonalization argument. So it's going to take this general setting and it's going to reduce it to Peck's diagonal setting. And I'll describe that argument now. So proof by diagonalization. And do the argument for just one equation, so you can sort of see the idea. So what you do is, so now we have one equation of odd degree, and it's some arbitrary equation. We want to solve it. So what you can do is you can take your equation and evaluate it at a sum of two vectors, x plus y. And then you can just do the Taylor expansion, right? So this is f at x plus, I'll explain what this notation means in a moment, up to 1 d minus 1 xy plus y. And these superscripts are the by degree. So you're expanding your monomials in x plus y of degree d, and you're writing them as something of degree d in x plus something of by degree d minus 1, 1, and so on. And so you do that, and our mixed terms, so all of the ones that have superscripts, you notice that the fact that d is odd means that one of these degrees in either x or y is going to be odd, and it's going to be smaller than d. So each fi d minus I has odd degree less than d in either x or y. Okay. Over here. So now here I'll sweep some details under the rug. So we're making the inductive hypothesis that you can solve odd degree equations of lower degree. And so these are equations of lower degree, of odd degree equations of lower degree, and so you can solve them in x and y. And so you can try and think through where I'm cheating a little bit here. Either look at Birch's paper or figure out how to really make this true. But essentially, by the induction hypothesis, you can find x0, y0 over Q such that all of those mixed terms vanish. So what does it mean that all those mixed terms vanish? It means that if we restrict x just to the subspace spanned by x0 and y0, so a and b are scalars, we get a diagonal form, right? A to the d times a scalar plus b to the d times another thing. Okay. Now, the same sort of, the same kind of argument can be taken further, and instead of just getting a two-dimensional subspace where this happens, you can get a bigger one. And so you find x1 to xn, where if you evaluate f on linear combination, then this is the sum is 1 to m of a to the d. Okay, and now, and these are all rational. And now we want to solve for the AI, and that we can do by Peck's theorem. Okay, so Peck implies you can solve for AI once m is large enough.
Sorry, you might have said this, but in both Peck and Birch's theorems, are ND and NDR like explicit, or there exists such a integer?
So in Peck's theorem, I think you can get something very explicit. In Birch's theorem, he doesn't give something explicit, and for good reason. But we'll give some balance.
Thank you.
Are there other questions so far? Maybe I just finished this proof, so maybe this is a good time to pause if there's another question. Okay, so a couple of remarks about what happens here. So one sort of, I guess, philosophical remark is that diagonal forms, so the forms that we're using, the good ones where we can actually do something are sparse, and that's a shame. Okay. Okay, this isn't a precise remark, but kind of a shame that those are the only ones that we can handle. The second thing to notice, which is going to recur later, is that even if we just wanted to solve one equation of degree d, we had to solve for all these mixed terms, right? So we ended up having to solve a bunch of equations of lower degree. So one equation of degree d gave rise to many of lower degree. Right. So yeah, so let me say a little bit about bounds for Birch's theorem. Maybe I should say, I don't remember exactly what the order of magnitude of the bounds are for Peck's theorem. Like somewhere around d squared at this point or something, or anyway.
At the time he did that, they were sort of I don't know, maybe 4d squared.
Oh, okay. So,
but these days you could get d log d, order d log.
Oh, okay. So yeah, so there's there's very reasonable bounds. I think by any measure for Peck's theorem for what this ND should be. Not so for Birch's theorem.
But what should the truth be for Birch's theorem?
Sorry?
What should the truth be?
So that's the hard question, right? Because if you want lower bounds, you need, so if you want to say you need at least this many variables, you need to have forms that don't have rational points. And I think that's sort of a very difficult question to prove that some equations don't have rational solutions. So yeah, I don't know if there's a conjecture.
Also, you haven't built in any local obstruction, so.
You mean because the degree is odd, or?
Yeah, I'm just in terms of the way you're formulating it, you always want solutions. You never said there's a solution if there's a local obstruction. So maybe I'm just saying, can't you use those if you're trying to make? There's a local and global question.
There's no reason why RD squared plus 1 might not be.
Okay, there's your answer.
So there's the conjecture.
That has been conjectured.
Oh, okay.
And
Okay.
what's the counter example in degree RD squared?
Can single form of degree D. Look at a norm form in D variables which has no solution mod P. And when you look at that plus P times another norm form of similar type in a new set of variables, all the way up to P to the D minus 1.
Okay.
It's a local obstruction.
Yeah, so it's the added obstruction.
Very good. 2, if it gets prime 2 or even degrees forms, I mean, they're really bad bound. I mean,
Yeah,
square is them,
degree
no wonder not.
exponentially bad. Yeah.
Okay. So yeah, I'm gonna write down some bounds that are nowhere near this. Okay, so the first, so like I said, Birch didn't give explicit bounds in his paper. The first bounds that I guess would be considered reasonable are for the general question. Schmidt showed that for cubics, it's enough to take 100,000 or to the 5 variables. And then Trevor Woolley has a couple of papers called Explicit Bounds for Birch's Theorem from 96, 98, where he works out and improves upon the Birch's original argument. And this gives for degree 5 an exponential bound. And then for degree 7, you get something tower type. Like this, where the height of the tower is mod r. However, you can throw something at me if I'm getting this wrong. And for higher degrees, this little box. In general, there's some recursive bound which comes out. So it sort of involves these highly iterated functions. Worse than power.
So Birch's original argument, is it also tower type bounds, or is it even worse? Or I guess how bad is
Trouble with
It doesn't make them explicit.
but if it were worked out,
Well, I mean, so Schmidt does better than Birch, and that is essentially an Ackermann type bound. Correctly. The bound I got is better than Ackermann, but you would never notice.
How does yours bound on D, or is that not?
Power exponential. So
So the result I'm going to talk about is recent joint work with Tamar and Ziegler and Andrew Snowden, and we show that for any odd D, you can take NDR and Birch's theorem to be bounded by a polynomial.
How does this AD depend on D?
So we haven't unraveled that yet. That sort of involves working out the arguments.
D is fixed.
Sorry?
If we think of D as fixed.
Yeah, but okay, so because of where is that? Because of this point, so even if you want to solve one equation of degree D, you need to sort of get reasonable bounds for this. So I think this will this should give, improved bounds for even one equation of degree 7 or 9 or so on.
But not
Once we work out.
B, and the B of D, okay, so it's
For now, yeah, for the talk today, certainly, yeah, D is fixed. But that's I mean, these can be made explicit. It's not yeah. Okay. So before
I'm just trying to clarify that it's polynomial in R, but not in D. That's all.
oh, certainly not. Yeah. It's those are gonna be more than exponential in D. I haven't worked it out, so I'm not gonna hazard a guess at what they will be. And before I talk about how what goes into the proof of this, I'll talk about a very general approach to this problem, which is due to Schmidt. So what does Schmidt do? So Schmidt made this very powerful creative definition of the strength of a polynomial. I guess the definition is simple, but it's surprising that you're able to do so much with it. So the strength of a polynomial, now this is a homogeneous polynomial, is the minimal S such that you can write your form as a sum of S products, where all of these have to be lower degree. And so you're writing it as a sum of reducible forms. You can also define this for a collection. You can and we will. So the strength of a collection F1 to Fr is the minimal strength of the forms in their pencil. So it's the minimal strength of any of these expressions where you're taking non-trivial rational linear combinations. And okay, so so this is one way to generalize the familiar notion of the rank of a quadratic form, right? And as an exercise to sort of digest the definition, you can show that if you take a diagonal form, so strength is at most n, that's just the definition, but its strength is at least n over 2. So that requires a bit of an argument. And what Schmidt showed with this definition is that instead of using diagonal forms like Peck does, you can use the more general class of high strength forms and get the same conclusion. So it shows that it's the strength of a collection is greater than CDR squared, and people are rightfully asking about the dependence of some of the constants here on D. So this constant is exponential in D. So under that hypothesis, the variety where the FIs vanish. Okay, so I'm going to write something which is not stated in this paper. So this has the risky dense pupils. Okay, so what does Schmidt prove in his paper? He actually proves something much stronger than this. So he proves an asymptotic formula for counting the number of integer solutions in boxes. And as far as I know, Skinner's paper called Weak Approximation for Number Fields from 97, I believe. So I'm going to say, so class Skinner 97. So Chris Skinner showed how you can, showed you can use, if you have this counting formula, so you can use it to prove weak approximation. So the embedding of your rational points, you can approximate any set of local solutions by a global solution, and in particular that applies to risky density. So
is your theorem at the top? Can you produce a risky density?
Well, not in general. We need some sort of condition like this, but it's going to be a sort of more flexible condition than this one. I don't have an immediate. I think you need some sort of condition to have the risky density, but I don't have an.
I guess a lot of the coefficients might be 0, and then you're producing solutions in some small part of the space. Yeah, of course.
Yeah.
You have to put some.
Right. So this theorem of Schmidt fits into sort of a more general framework of subsequent theorems, where the general principle is that you have polynomials of high strength. Then they exhibit kind of regular behavior, or they behave kind of like you would expect from a random polynomial. And this has a bit of a funny history. So this definition has been redefined by Green and Tao in higher order Fourier analysis, and then by Ananian and Hochster in a question in commutative algebra. And so the name is also, so the name strength was coined by Ananian and Hochster. It seems like a good name, so I'm using that name. Schmidt called this the H invariant. But in all of these different settings that it's shown up, this is sort of this general principle. And that theorem is the first example of it. And one thing you can deduce from this theorem is you can get a new proof of Birch's theorem. So how does that yeah, so, okay, so if you want to use that theorem to prove Birch's theorem, instead of diagonalizing, so instead of replacing your collection by diagonal forms, what you're going to do is you're going to replace your original collection by forms of high strength. We call it process regularization. And again, I'll sketch the argument just for one equation. So if you have one equation of degree d, you want to produce solutions. So maybe you're lucky and it's high strength. All right, then you're done because your rational points are Zariski dense. And otherwise, by definition, your form decomposes as the sum of a few products. You can write it as gi times hi. Not too many of those terms. And because this had odd degree, then one of those is going to have odd degree. Right, so let's label them such that the GIs have odd degree. And then instead of looking for rational solutions to f equals 0, you can look in the subvariety where the GIs match. Okay. So now, what do we do? Well, the only thing to do, you look at the strength of the GIs, and hey, maybe we're lucky and Schmidt's theorem applies. Now these GIs have lower degree. So let's say they have degree d minus 2. Okay, but that's the sort of the key point, that they have lower degree, right? And maybe the Schmidt's theorem applies, then we're done. Because we get lots of rational points. And otherwise you keep going, right? So otherwise, keep going. So at every stage of this argument, the degrees.
Why d minus 2 and not d minus 1? Stupid question.
No, it's because they were taking the odd degrees. So if you had like originally like a degree 5 equation, then in the decomposition, you might have forms of degree 4 and 1. So you take the degree 1 part, and you might have 3 and 2. So you take the degree 3 part. So it's going to be it's the largest odd number, which is smaller than d.
Okay. Goes down by 2.
Right. So this okay. So this works, right? The degrees keep decreasing, and you might wonder, what happens at the end. You might have a bunch of linear forms, but that's fine, right? If you have a linear subspace which is non-trivial at the end, then it has rational points. Problem is, you might have a huge number of linear forms at the end of this process. And so, so it doesn't improve the bounds. But one thing that this does improve is that you can do a easy dimension counting argument and check that a generic form does have high strength. As opposed to, the previous case where generic forms are not diagonal, it is true that a generic form of degree D going to have strength at least n over a constant depending on D. Okay, so again, this is a philosophical remark, but on the philosophical level, we're much happier.
Generic means of Zariski dense.
Yeah, it's open dense. Yeah, because this is just the dimension count.
Yeah.
So again, there's this theme that we had before, which is that if you have a single equation of degree D, then you get many equations of lower degree. And okay, so this is similar to before. This at least philosophically looks better. Unfortunately, this process is very inefficient. And so we don't get any better balance for Birch. Okay, so this means no improved balance.
What did Schmidt do? Schmidt improved it, so he has another idea.
Schmidt improved what? Right.
This is Schmidt's idea.
So okay,
When you're saying you're not improving on Schmidt.
so if you so Schmidt proved something stronger. So Birch proved infinitely many rational points. Schmidt proved a lower bound for counting them in boxes.
Okay, I'm asking about the dependence. I mean, you said this is inefficient.
Yes. So we're going to address that
And
inefficiency.
you don't improve bounds for Birch. What bounds are you comparing to Schmidt?
I'm saying, so this is not something Schmidt does in his paper, this argument that I just described. I mean,
He does, right? So he has.
maybe I don't understand the question.
we kind of.
Schmidt deduces something stronger than Birch's result.
Okay.
But he also deduces a version of Birch's result by exactly this. This argument.
Yes.
Okay. So far, Schmidt's argument is what it's saying. You're saying this is inefficient. I'm asking what Schmidt did to make it efficient.
From before, essentially.
What Schmidt did to make it efficient? Nothing.
So this gives Schmidt's bound.
Yes.
Oh, okay.
Schmidt.
Okay.
Yes.
That's okay.
I mean, here Schmidt gets a quite explicit and reasonable bound. But in that argument,
I think the point is you have two Schmidts of the second board at the bottom. I think that.
oh, sorry, yes, this is a different paper.
Oh.
This is for cubics. Yeah. So right. So if you do this when you have cubic forms in the beginning, then when you decompose them, you're getting linear forms.
Right.
And then you can just restrict to that subspace. So
I mean, the corollary is a new proof of Birch's theorem. And in principle, Schmidt would produce better bounds than Birch would get. It's just that Birch's bounds were inexplicit. So it's
Okay. So
and actually Schmidt's argument is defective. So it's actually difficult to compare them.
Okay.
so this may produce a better Ackermann type function.
It would produce a better,
Okay.
a better bound.
Okay.
So one comment actually about the
Yeah.
generic forms. So of course Birch has this subsequent paper, which is a version of the circle method, focusing on non-singular
Yes.
forms, and of course that also applies, generic forms are non-singular. So
Yes.
and that would give better explicit bounds for the number of variables.
Yeah, that's a paper.
Yeah. Yes. Okay, so So this inefficiency of the process we described here is what I want to address.
Conditional singular. It's allowed to be singular, but it's conditional dimension of the singular.
And so
I don't even know.
How does this PE depend on D?
which one? And Schmidt's
Which one's
theorem?
independent? of D?
Yeah, I think you could, it's like 2 to the d times d factorial or something. It's some exponential function.
Doubly exponential.
Double exponential? Oh, sorry. Okay, double exponential. So yeah, so the new tool, the main new tool that we use to address this is something we call relative strength. And this was introduced by myself and Ziegler in 2021. And like I said, strength has these sort of various applications. We introduced this in distribution of polynomials over finite fields, and these questions in higher order Fourier analysis. And here's the definition. So this is sort of a more flexible generalization of strength. So now you have a collection G1 up to GR, and you have some F, and the relative strength of F relative to those G's is going to be the minimal strength of any form which is equivalent to F mod G. So degree of F equals degree of FL, and their difference is an ideal. And this definition, whoops, is a little bit of a mouthful.
So these GIs don't have any imposed degree.
Right, they could be higher degree. It's interesting when they have lower degree than F. Yeah, but yeah, everything is homogeneous. And maybe a more digestible way to say this is that Schmidt's definition of strength, it makes sense in any graded ring, right? We're asking how things decompose into lower degrees. And this is that same definition, just in the ring, the coordinate ring where you mod out the GIs. And our main result, sort of the analog of Schmidt's result in this setting, I'll state a special case of it. Case. So this is the first special case where we get something new. So now we're going to have.
Is this related to slice rank at all?
Well, slice rank requires that one of the terms be linear. So I think they behave quite differently. But, so here we have some quintics. So these have degree 5. And we have a bunch of cubics, have degree 3. And I'm writing little r and big R, and you should really think of big R as being much, much bigger than little r. And our hypotheses are that the strength of the cubics is larger than some polynomial in the total number of equations, and the relative strength of the quintics is larger than some than the same polynomial, say, but only in the number of quintic equations. Okay, so I'll go through this in a moment after I finish writing it. Then under these hypotheses, the rational zeros of the Fi and the Gi are Zariski dense. So 0 that's dense cuboids. Okay, so the sort of key the key thing in this theorem, which if you take away the FIs, then this looks identical to, if you take away the second condition, it just looks identical to Schmidt's theorem. But the key here is that the second condition is this threshold is independent of big R, of how many cubics there are. And that turns out to be very important because it means that this regularization process that we ran here, now let's say you started with some quintic equations and some of them broke down into cubics. It doesn't matter how many cubics there are. That doesn't affect how many quintics, sorry, that doesn't affect the sort of number of cubics that you might have to add at the next stage. And so this ends up giving rise to an efficient regularization process. Gives you a bound which is only polynomial in the number of equations. So what comes out of the added flexibility in the hypothesis is that color. So this gives us an efficient relative regularization process. And as a result, we can get, so from this theorem, we can get polynomial bounds in degree 5 for Birch's theorem. So N5R is bounded by some polynomial. But in general, we can, it's a little bit more complicated to state the general hypothesis, but we can get polynomial bounds in every degree. So
the risky density is used.
Yes.
Maybe you can say a word. So put that into that lemma. The general theorem.
Yeah, I mean, yeah, this is our main theorem. So deducing these bounds from that theorem is easy.
But you use the risky density.
But to prove this theorem inductively, so I'm going to sort of sketch the proof of this theorem.
All right.
All
right, then we'll.
And we'll see how you need the risky density. So if you knew, for example, that if in Schmidt's theorem you only knew that a condition like this implies the existence of rational solutions, then I couldn't prove existence under the theorem. But if you know the risky density, then you can get somewhere. Okay, so all right, so let's have almost 15 minutes. So I'll sketch the proof of this theorem. Well, I'll give a high-level sketch. And I'll start by stating the sort of main new technical result that we need to prove in order to get this. And after that main new technical result, the other engine which is going to drive the proof is Schmidt's theorem. Okay, so we're not only taking inspiration from this, but we're using it in the proof.
What kind of tools did Schmidt use for his theorem?
Yeah, so this is the circle method. So we got the sort of very sophisticated version. He showed the circle method can be used. But once we have that, we actually don't need to use harmonic analysis at all. So there's no integrals in our proof. Schmidt has fortunately done them all for us. Okay, so the main new technical result that we need here is that under the hypotheses of that theorem, we can show that the following map. So this is going to be the map where you take a tuple of vectors and you restrict your cubics to the subspace you span. So here I'm using this notation for cubic forms and m variables. And if you had r cubics, so maybe you have r cubics and m variables, and you're also restricting to the quintex. Okay, so you have this map, this restriction map, which, you know, implicitly this was showing up already in Birch's argument, right? Under these hypotheses, we show that this map is projected. Okay, so I didn't tell you what m is. So we're going to need it for m, which is on the order of little r squared.
So there's big M and little m.
There's big M and little m.
Big M is an exponent there, and little m's are inside the C.
Yeah, so we're taking a tuple of m vectors here. So these are originally polynomials on Cn. And then we take the subspace spanned by these m. So maybe let me write this map explicitly. So if we have some gi, then this is going to take a tuple of vectors x1 to xm. So it's going to take this to, say, for just one cubic. And we get a new polynomial in m variables, res x, I'm calling it restriction to x of g. And this polynomial in m variables, when you plug in m variables, it's just g at that linear combination.
Sorry, in the definition of strength and all this, do we have Q coefficients?
In these definitions, yes.
And here we're working over C now.
Yes.
Okay.
So a lot of the work is to show that it doesn't matter too much, if you allow. But is this, I do want to make sure the definition of this map is clear. So what this map is doing is it's taking a tuple of vectors, and it's replacing the polynomial on the whole space by the polynomial restricted to their subspace by a formula like this.
If there is a big M or small, or everything over there?
I don't think there was a big M anywhere. These are supposed to be the same. Yeah, maybe my handwriting isn't great, but these are M's are all
Same M.
yeah. Yeah. Oh, sorry. Yes. These should all be small F's. Yes.
Medium man.
Yeah. Okay, so we have this. Restriction map, and this is like you said. There's in these hypotheses, I'm looking at decompositions. The definition of strength is being taken over Q, but here this is a geometric result. This is that's why I wrote C explicitly. We're talking about the mapping surjective on Ziegler.
I'm confused. So
Yeah.
M on the order of R squared, little m on the order of little r squared.
Yes.
There's no big R in the surjectivity condition.
Well, I mean, in the hypotheses, we have a big R, but we're gonna. Okay, so the bigger you take little m, the harder it is for us to prove things about this, because it has more coordinates, and what we show is that the coordinates are regular sequence. We only need to take m this big.
And what was n again?
N is just the ambient dimension.
Of what?
Those, so these are all. Okay, so we have this map which is surjective, and once we know that, oh, and sorry, I'll say I'm only going to prove, so the statement of the theorem is that the rational points are dense. I'm only going to prove that the existence of rational points. And it's only marginally more effort to get that they're dense, but I think it'll be clearer if we just prove they exist.
Amichai, I have another question.
Yeah.
What is exactly the range of this map? Like I understand the map itself, I understand very well.
Yeah.
It takes vectors, types of vectors, and give you new polynomials, right?
Yeah.
What is the space that we want to surject on?
The space of all tuples of cubics and m variables and tuples of quintics and sorry.
And this uses this strength assumption.
Yes. Yeah. So now that we know this, and together with the previous comment about forms of generic forms having large strength, so you can deduce that if you choose U1 up to UM generic, but okay, it's going to be a dense open set of those tuples with their span contained vanishing locus of the cubics. Okay, so this is a closed condition, tuples of vectors whose span on which the cubics vanish. And sorry, I wrote generic twice. And in that closed set, there's a dense open set where the second tuple of coordinates is going to be generic, surjective. So we get that the strength of the degree 5 guys restricted to U is just like the strength of a generic collection of forms in M variables. And this is again, just by dimension counting, this is a lower bound for there's some constant here depending on the degree, which is 5. So this is a lower bound for the strength of a generic form in M variables. And because we chose M to be some large constant times R squared, so this is also going to be order of magnitude of R squared. Okay, and now we'll see in a moment why I want this R squared here. And so now we can apply Schmidt's theorem, which I unfortunately.
I'm missing something about the rationality.
It was just a fluke that Schmidt's theorem ended up in the right place. So now this R squared is going to be that R squared in Schmidt's theorem. Okay. So first we're going to apply Schmidt in degree 3 to get that if this happens in a dense open set, then we can actually find a rational point in that dense open set. So you can take the subspace U to be rational. Okay, so now we've used Schmidt once. And now we're going to use Schmidt's result again in degree 5. After we've restricted to this rational subspace, we now have this collection of degree 5 equations restricted to that rational subspace, and they satisfy the condition of Schmidt's equation, of Schmidt's theorem. And so we get that those guys have a rational solution. Okay, so we've used Schmidt here twice. Yeah, so Schmidt does a lot of the hard work, and the main novel technical result, like I said, is this one, to get this geometric result from the hypotheses. And let's say how I'm on time. It seems like a good time to end. So yeah, thanks for your attention.
Yeah, thanks, Ami, for the wonderful talk. Are there any questions?
Seems to me you have to explain that proof.
This part.
Yeah.
Yeah. Okay, so I break it up into two parts. So one is something that we showed in this 2021 paper, which is that if you make this hypothesis, but where the strength now is being defined over C, then this holds. So then your collection is a regular sequence, and therefore this holds. And the new work in this paper, I mean, besides this argument is new, but the new work in this paper is to show that you don't lose too much. So the strength, when you extend your field, you can allow for more decompositions, right? And the strength can decrease. Something irreducible can become reducible and so on. But we show that you can't lose too much. So we show that the loss between going from strength over Q to strength over C isn't too bad. And so it's enough to assume this hypothesis over Q.
How do you do that? I mean, is there some extension you go to, or that you bound some?
Okay, so I haven't prepared a succinct answer to that question. But yeah, I mean, basically we reduce the question to multilinear forms. So you can, all of these things you can, just like, going from a quadratic to a bilinear form. So you can reduce all of these questions to the multilinear question, and strength doesn't change.
Yeah, because eventually it's a linear issue.
Yeah, the end of the base of the yeah. But when you have this question for a collection of multilinear forms, then you can. Yeah, sorry, I don't have a 1 minute answer to that question.
You said that this started with thinking about this kind of question in the function field case, or not?
Well, we were thinking about. Okay, so I mentioned Green and Tao redefined strength, and in the context of what's called a higher order Fourier analysis. So they were looking at polynomials over finite fields in many variables, and they show that polynomials that have high strength have well-distributed values. So that's what they showed, and the bounds there were bad for the relationship between the strength and the distribution of the values, and we were working on improving these bounds. And eventually, that was done without using this relative strength thing, but this gave another way to do it, and we got this efficient relative regularization process, and we kind of had a few problems that we were hoping to use it for, where that natural regularization process showed up, and so yeah. So I don't know if that answers your question. You're asking what the original problem that we were thinking about was? Yeah. So that original problem was the relationship between the strength of a multivariable polynomial over a finite field and the distribution of its values. So high strength implies equidistributed. And originally there were bad bounds, and the original proofs used a regularization process like this one. So we wanted to improve that. But that was eventually done without requiring this.
And so back to slice rank, the slice rank is G's linear?
Yes.
That was, of course, used in those things, but they came with a nonlinear version as well. Emoji.
Yeah. I think slice rank is it's sort of substantially different somehow in that. Okay, for example, the locus of forms of bounded slice rank less than 100 is closed, and this is not true. It's known to be not true of this rank. It's sort of much more nicely behaved.
Okay, so you were not doing this kind of problem with rationals replaced by FP of T.
No, we weren't.
And is that an interesting question?
Yeah, that might be an interesting question. I haven't looked at that.
I think for the outcome, not so much, right? Because FP of T is a free field, so you know you have really good bounds on existence of rational points just from bank 10, which you know all about, Nick.
But for Zariski density, there's sort of good technique.
I guess you can deduce results in the same way. So one question. So Schmidt has this quadratic in our difference, which you're using. So presumably, these ideas that Simon, Rudd, and Myerson has used in second Birch would reduce this to linear dependence on our.
Yeah.
Would that actually have a significant impact, or is it all sort of swallowed up by other complexities?
Yeah, I think it would be swallowed up because there's sort of a lot of a intricate induction going kind of into these things, and we have polynomial loss, I think, at a few stages. So I don't think that would have an appreciable. You wanted to ask something?
Yeah, since some people mentioned FP, is it possible to prove this kind of surjectivity using any Lefschetz principle for like statements and characteristic P?
So we actually this was I think Elon asked about this about. Okay, so this statement that I made here, I said that first we prove it over if you take the definition of strength over the complex numbers, and that since then we have another proof, a more direct one, but we do that go through finite fields, which is I think what you meant, right? So that statement, yes, but the statement that you don't lose too much going from Q to C, that's sort of an arithmetic statement, yeah.
Are there any further questions? If not, let's thank